Hi everyone, it's Michael. So I have a very challenging problem for you all today. This problem was from the 2012 IMO Shortlist, and it was number 6 on it, so one of the harder problems. And it took me a while, but I was eventually able to solve it. So if you'd like to try to figure it out yourself, feel free to pause the video. Alright, so I'm going to go over the solution. So we have a triangle ABC with circumcenter O and incenter I. And then the points D, E, and F lie on the three sides of the triangle, BC, CA, and AB, so that BD plus BF is equal to CA, and CD plus CE is equal to AB. And then the circumcircles of BFD and CDE intersect at P, and we want to show that OP is equal to OI. Alright, so the picture looks fairly simple. But the key is to figure out how to use this condition on the lengths. So how do we use the fact that BD plus BF is equal to CA and CD plus CE is equal to AB? So I'm going to get into that a little bit later, but before I do that, there's a couple things that we can do before we begin working on that. So one thing that I notice is BI is an angle bisector of angle FBD. And we know that the angle bisector of an angle in a circle meets that circle at the midpoint of the corresponding arc. So I'm going to draw in line BI, and I'm going to let it meet the circumcircle at H. And so H has to be the midpoint of arc FD. So I'm going to mention this later on. And I'm going to do the same thing with this circle, so the circumcircle of CDE. So if I draw the line CI and I let it meet the circumcircle at point J, then J has to be the midpoint of arc ED. Alright? But before I write that out, there's something that we can notice here. And I think this actually might be a well-known kind of theorem, because I feel like I've seen things like it before. But it turns out that IHPJ is cyclic. And you can prove this using a fairly simple angle chase, which I'm going to do now. But that seems like it might come in handy because we want to show that OP is equal to OI. If it's true that IHPG was cyclic, or IHPJ, then that would mean that O would have to be the center of that circle. So let's see if we can show that that's cyclic. All right. So I'm going to calculate angle HPJ and show it's 180 minus angle HIJ. So the configuration of the problem actually could potentially be different, where if P, for example, lied over here, then I'd have to show HPJ is equal to HIJ. So there's really two different configurations, so I'm just going to sort of gloss over that in the solution and just show the way it is here, where I want to show that angle HPJ is 180 minus HIJ. Okay. So we have angle HPJ. It's equal to angle HPD minus angle JPD. Okay. And HPD, that's 180 minus HBD, because HBDP is cyclic. Okay, so this is 180 minus HBD. And then angle JPD is the same as angle JCD. That's because JECD is cyclic. And so we have 180 minus HBD minus JCD. Well, those are two of the three angles in the triangle BIC. And so they have to add up to the exterior angle, which is angle HIC. So 180 minus both of those angles has to be 180 minus HIJ, which is the exterior angle. So we have angle HPJ is 180 minus angle HIJ, and so that means angle HIJP has to be cyclic, or quadrilateral HIPJ has to be cyclic, I should say. So what's really interesting about this is we never use the fact that I was the incenter, and we didn't use this sum condition either. So I think this might just be a well-known fact. If you have two circles arranged like this that pass through the vertices and a common point on the side, and any point, because we didn't use that I as the in-center, then with this configuration, you always end up having HIJP as cyclic. All right, so I'm going to draw that in. So where do we go from here? Well, like I mentioned, H is the midpoint of arc FD because BI is an angle bisector. So HF has to equal HD, so I'm going to write that out. Okay, so since BI bisects the angle, HF is equal to HD. And then, so I'm going to use this later, but if K is the midpoint of FD, then HK is perpendicular to FD by symmetry. Okay? All right. So actually, so here's my plan. I'm going to draw in a few more points. So I just drew the perpendicular from I to BC. So what's my plan here? So I know HF is equal to HD. And I want to take advantage of the sum condition given in the problem statement. Now there's a certain trick, and I've seen it used just a couple of times before, but using Ptolemy's theorem, you can get sort of a sum in an equation, as long as you know that these two sides are equal. So I've actually never used Ptolemy's theorem before on my channel. I feel like it's not used that often, but every now and then you do see it come up. So I'm going to write it out here. But actually, before I apply Ptolemy's theorem, I'm going to explain sort of what I have in mind. So I am going to try to, so I'll just show the next couple steps. But I want to show that triangle HFK is similar to triangle IBL. That's not too hard to show. We know HK is perpendicular to FD, where K is the midpoint of FD. That's true by symmetry, since, like I mentioned, H is the midpoint of arc FD. Okay, so I'm going to draw that in. So that means that angle HFK has to equal angle HFD, which is HBD, which is angle IBL. And from there, it's easy to see that triangles HFK and IBL are similar, okay, because they both also share a right angle. And so we have, so here's a similarity, and I just drew in an HF. And so we have, so now I'm going to apply Ptolemy's theorem on quadrilateral BFHD. And the fact that HF is equal to HD is going to come in handy here. So we have, Ptolemy's theorem says that the product of the diagonals in a cyclic quadrilateral, so in this case BH times FD, it's equal to the sum of the products of the opposite sides. So BF times HD plus BD times HF. So I might do a video on this later because I've never done one on it. But this is the first time I've applied it on my channel. Okay. And we know HF is equal to HD. So if we set this HF equal to the HD, we can then factor it out. Or actually I did it the other way. I set it HD equal to HF. So we can pull out the HF, and here we get the sum that we wanted. So D plus BF, we get that sum right here. Okay, so this is really the key step, I feel like, where you use Ptolemy's theorem to take advantage of the sum condition. So it's a little bit tricky of a way to take advantage of this, but I haven't been able to find another way or another solution that takes advantage of this in a way that doesn't use Ptolemy's theorem. So if you have an idea in mind, I'd love to see it. But this is kind of my idea of how I thought to take advantage of Ptolemy's theorem, or take advantage of this sum condition. Okay, so we have that this quantity is equal to BF plus BD times HF, since we can factor out the HF, since HD is equal to HF. And then BF plus BD is equal to CA. So we have BH times FD is equal to CA times HF. Okay. So now I'm going to rewrite this in a way that takes advantage of the similarity. So I'm going to solve for BH. So BH, it's equal to CA times HF over FD if you divide by this FD. But HF over FD, that's HF over 2FK. And HF over FK, we can use the similarity that we just found. HF over FK is IB over BL. So we have that BH is CA times IB over BL. Okay? Now this is really interesting because CA, if you think about it, in the original problem, we can sort of choose where D lies on side BC. And then based on these two sum conditions, that would tell us where E and F lies, and that would tell us where the rest of the figure lies. But this expression right here, AC, does not depend at all on the choice of D that we chose. And neither does IB, and neither does BL. So this expression here is the same thing no matter where we choose D, E, and F to be, which is really surprising in my opinion. Okay, so the length BH, it depends only on the triangle ABC. It doesn't depend on where we choose D to be, E and F to be, as long as they satisfy the sum condition. So basically we could move D along point BC and the length BH would be the same. And I claim not only does the length BH have to be the same, but the point H has to be the same point, because H lies on the line BI, which is independent of the choice of D. Okay? So since H lies on the line BI, and that doesn't depend at all on D, if the length BH doesn't depend on D, then H doesn't depend on D. Then by the exact same argument, J also doesn't depend on D. And so if H doesn't depend on D, J doesn't depend at all on D if we moved it around. And so I also obviously doesn't depend on D. And so the whole circumcircle here doesn't depend on D. So this really surprised me when I first saw it. But I'm going to show you. I'm going to move around point D a little bit, and you'll see that this circle, the circumcircle of IHJ, it doesn't change. So that's another position of point D. That's another position of point D, and this circle's still in the same place. That's another position of point D. It looks a little wacky moving it all the way over here, but the circle stays exactly the same, which I thought was really surprising. Okay. All right, so that's a bunch of different configurations. The circumcircles IHJ always stays the same, so I'm calling it omega. And basically, I want to show that OP is equal to OI for any given choice of D. But I know the circle is always the same, and I know P is always going to lie on the circle. So that basically means we want to show that O is the center of the circle. So we've shown that I, H, P, and J lie on a circle, but we need to show that O is the center of that circle, which is the same wherever D is. So then the question is there a place where we could move point D to so that it would make the problem easier? Because if we could move point D to a certain position, and we could show that IO is equal to OP in that position, then that would mean that O is the center of the circle for that particular position of D, and so it would have to be for any other choice of D. Okay? So it turns out that there is a good choice for point D. And what it is, so I'm going to let M be the midpoint of BC. And for those of you that know about X centers, you'll know that the reflection of L over point M is the point of tangency of the AX circle with side BC. Okay? So that is actually, believe it or not, the good choice for point D. So I'm letting L prime be the reflection of L over point M. And this is the point of tangency of the AX circle with BC. Although I'm actually never going to use that fact. So that's initially how I solved the problem. So if you know a little bit about x-centers, it makes the problem easier to solve. But then after I looked at it for a little while, I realized you don't need anything about x-centers. Okay, so I'm going to let D coincide with that point, L prime, which is the reflection of L across M. And omega, it stays the same because it's always the same wherever D is. And we want to show in this configuration that O is the center of omega. Okay, so how do we do that? So first, I'm going to draw in the end circle, and I'm going to draw in the points of tangency of the end circle. And I claim that not only is D the reflection of L over M, but these sum conditions guarantee that E and F are also the reflections of the tangency points of the end circle with respect to the midpoint. So in other words, E and F are also where the x circles are tangent to the sides. So I'm going to prove that here. So we have CE, it's equal to AB minus CD using this condition. Because basically, you can think about it, we can move around point D, but then E and F are a function of point D based on these two conditions. So if D is at this point, it forces CE to be AB minus CD, and that's AB minus BL because D and L are symmetric with respect to the midpoint. So CD is equal to BL, and then AB minus BL, that's AB minus BQ, which is just AQ, which is just AN. So we have CE is equal to AN, so E and N are symmetric with respect to the midpoint of AC. And the same is true with F and Q. So I'm going to draw this in. Okay. So E and N are symmetric across R, and so are F and Q. So the figure has a threefold symmetry. Okay. So I'm going to hide a bunch of things now. But I claim that this point P, it actually has to be PD is perpendicular to BC, PE is perpendicular to AC, and PF is perpendicular to AB. So I'm going to show that property right now, and I'm going to hide a bunch of things for now. So I'm going to let P prime be the reflection of I across O, and then I claim that P prime is actually the intersection of these circumcircles BFD and CDE. And so I'm going to explain why. But if P prime is the reflection of I across O, we have a lot of symmetry in this figure. It's almost seems very easy to see visually that it has to be perpendicular to all three. Because I, L, and OM are both perpendicular to BC. And since D is the reflection of L across M, and P is the reflection of I across O, then P prime D is clearly perpendicular to BC. So I'm going to write this out. But first I'm going to draw in a few segments. Okay. So since IL is perpendicular to BC, and we also know that IN is perpendicular to AC, IQ is perpendicular to AB. But not only that, clearly the orthocenter, if you draw the line to the midpoints of each of the sides, it has to be perpendicular. And so by the way we define P prime, since P prime is a reflection of I over point O, and IO is equal to OP prime, since we also have LM is equal to MD, it's very clear to see from there that P prime D has to be perpendicular to BC. So the full proof would involve writing out proportions, but it's fairly easy to see. So P prime, if you connect it to D, E, and F, it has to be perpendicular to the three sides of the triangle. And with all those right angles, we have cyclic quadrilaterals. So that means that BF P prime D has to be cyclic, and CE P prime D also has to be cyclic. And if those two are cyclic, then that means that P prime, it's actually the intersection of the circles through BFD and CED, which is exactly what's given in the problem statement. So for this choice of D, that means P prime is equal to P. Okay, so P prime is equal to P for this particular choice of D. It's the intersection of these two circumcircles. But we said that for any choice of D, I and P would both lie on this circle, the same circle omega that doesn't change. So if I and P are on that same circle omega, regardless of where point D is, then since O is the midpoint of IP, O has to be the center of omega. And if O is the center of omega, and omega does not depend at all on D, then that means OP has to equal OI for every choice of D. And that solves the problem. So this had a really interesting trick to solve it. It used the fact that wherever point D is, a bunch of the configuration is going to stay the same. I don't know if I've ever used something like this to solve a problem on my channel, but it's a really cool idea. And if you know a little bit about X centers, I'd recommend trying to find the proof I mentioned involving that. So this is probably, I think, the second hardest problem I've had on my channel, maybe second to the video on the 2019 IMO problem 6. So if you like this video, give it a thumbs up. And if you'd like to see more like this, feel free to subscribe to my channel. Thanks, everyone.